Usually, when we call something astronomical, we mean really big. Last time we tried to get a grip on the immensity of the universe by zooming out 26 orders of magnitude. Just as crucial for astrophysics, though, are the orders of magnitude smaller than human scales. The smallest and the largest scales of the universe are deeply connected. I'll give you a few examples that we'll be exploring in the lectures to come. With the technique of spectroscopy, we can figure out what the stars and planets are made of, but only if we understand how atoms interact with light. Stars derive their power from nuclear fusion, the melding together of light elements into heavier elements. So, we're going to need a crash course in nuclear physics. And when the sun runs out of nuclear fuel, it'll become a white dwarf, a dense ball of carbon and oxygen that's prevented from collapsing by Heisenberg's uncertainty principle, a key element of quantum theory. With all that in mind, in this lecture, we'll zoom inward rather than outward, all the way down to the realm of fundamental particles. To start, let's remind ourselves about what's probably the most familiar of the four fundamental forces of nature: gravity. It's what keeps us pinned here to the surface of the Earth. Every mass attracts every other mass according to Newton's law of gravity, which says that the force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. The constant of proportionality is big G, Newton's gravitational constant, which has a value of 6.7 times 10 to the minus 11 Newton meters squared per kilogram squared. Let's suppose we have a big mass, big M, held fixed at the origin of our coordinate system, and little m is free to move, like a planet orbiting a star. Little m will feel a pull toward the origin, and to convey the direction of the force, we'll use vector notation. A vector is an arrow with a magnitude and a direction. We put a little arrow over the F to remind us it's a vector, and by convention, a hat on top means it's a unit vector, a vector with a magnitude of 1. So all it's doing is specifying a direction. R hat points in the direction of increasing r, that is, away from the origin. But the force is toward the origin, which is why we have the minus sign. The acceleration vector points in the opposite direction as r hat. We'll be using Newton's law of gravity a lot. We'll also need the formula for the potential energy associated with the gravitational force, which varies as the product of the masses but goes inversely with r as opposed to r squared. And again, it's negative. Does that make sense? Let's see. If we let little m fall toward the origin, r shrinks, and according to the formula, the potential energy becomes more negative, which implies that positive energy must be showing up somewhere else, since the total energy is conserved. And that does make sense. The kinetic energy, 1/2 mv squared, is increasing as the mass accelerates toward the origin. The gravitational potential energy is being converted into kinetic energy. So that's gravity. Now let's start zooming in. And just like last time, we'll zoom logarithmically. With each step, we'll magnify by a factor of 10. We'll start here on the human scale, where things are measured in meters. Zooming in to 1/10 of a meter, we're now centered on my face. And as we keep narrowing our field of view to 1/100 of a meter, 10 to the minus 2, we're staring into my eye. Another factor of 10 to the millimeter scale, and we can fit right through the pupil of my eye and dive inside. At 10 to the minus 4 meters, we can see the blood vessels in my retina, and by the time we hit 10 to the minus 5, we're seeing individual blood cells. Now we're at 10 to the minus 6 meters, a millionth of a meter. That's a unit that comes up often enough we give it a special name, a micron. Here we can see individual bacteria. Each one is a few microns across. And starting here, the lighting looks strange. Everything's blurry. There are fringe patterns all around. That's because we've zoomed in to the size of the wavelength of light. Light is a wave, an oscillating pattern of electric and magnetic fields, but it's hard to tell way up on human scales because the wavelength is only about half a micron. Down here, though, it's obvious. Light waves bend and spread like water waves, and it's impossible to focus them sharply. That's the phenomenon of diffraction, which will play a big role in our later lectures on telescopes. For now, though, let's just pretend we can see normally and keep going. After another few orders of magnitude at 10 to the minus 8 meters, we start to see that the water that surrounds us is not a continuous fluid. It's made of individual molecules. You might remember molecular molecules from chemistry class, made from balls and sticks like Tinker Toys. But real molecules don't look solid. When we zoom in to 10 to the minus 9 meters, that is, the scale of nanometers, molecules look fuzzy, and they're in constant motion, jiggling and vibrating. They're getting knocked around by other molecules. The energy of all those random motions is what we perceive as heat way up on human scales. The hotter the material, the more vigorously the molecules are bouncing around. Zooming in closer, we see that the individual atoms that make up molecules. Let's look at a single water molecule. It's made of 2 hydrogen atoms and an oxygen. In fact, let's snuggle up right next to the oxygen atom. Like any atom, oxygen has a nucleus, which has a positive electrical charge, and it's surrounded by orbiting electrons, which have negative electric charge. Because of those opposite charges, the nucleus and the electrons are attracted to each other, which brings us to the second of the 4 fundamental forces of nature, electromagnetism. Here, the relevant equation is Coulomb's law, which says that the electric force goes as the product of the charges divided by r squared. So it's very similar in form to Newton's law of gravity. For the proportionality constant, we'll use the Greek letter eta, because the word electric comes from the Greek electron, which starts with an eta. I should add, though, that I made up this notation. More often, you'll see that constant written as 1 over 4 pi epsilon naught, but that's needlessly complicated for our purposes. Numerically, eta is 9 times 10 to the 9 Newton meters squared per coulomb squared, where the coulomb is the standard unit of charge. In those units, the electron and the proton both have a charge of magnitude 1.6 times 10 to the minus 19, which we'll represent with the letter E. Also, notice the force law has a plus sign this time, not a minus sign. When the product of the charges is positive, that is, when they're both the same sign, then the force is repulsive, pushing the charges apart. When the charges have opposite signs, like an electron and a proton, they attract. We can also write down the potential energy associated with the electrical attraction or repulsion. That's the so-called Coulomb energy, which, as in the case of gravity, varies as 1 over r. Now, back to the oxygen atom. The Coulomb force explains why the electrons are attracted to the nucleus, but there must be something else going on, because otherwise, why don't the electrons fall all the way down onto the nucleus and neutralize it so that it comes to rest? Well, we might ask the same question about the Earth. If the Earth is attracted to the sun, why doesn't it fall in and burn up? The answer in that case is that the Earth has a non-zero angular momentum, a sideways velocity in ordinary language. And the gravitational acceleration just keeps turning its velocity vector around in a circle. So, when we look closely at an atom, we might expect to see the electrons whirling around the nucleus like a miniature solar system, but we don't. Instead, the electrons look indistinct. There's an electron cloud surrounding the nucleus. That's because electrons, like all fundamental particles, obey the rules of quantum theory. the counterintuitive laws of motion and interaction that are more exact and fundamental than Newton's laws of motion. Here's what quantum theory says. When we measure the location of an electron or any fundamental particle, we get a specific answer. But when we're not measuring it, when we're not forcing the question of where it is, the electron spreads out into a cloud. And there's no way to predict exactly where we will find it when we do measure it. All we can say is that we're likely to find it somewhere in the cloud, or to use the technical term, the wave function. That cloud is called a wave function because the equation that governs the size and the shape of the cloud, how it moves and interacts with other clouds, resembles the equation for ordinary waves. And, like regular waves, the wave function can take the form of a pattern moving through space with a certain speed. It can even interfere with other wave functions, producing fringes, like when water waves overlap. Now, in the case of an electron near the nucleus of an atom, the wave function isn't moving. It's trapped by the electrical attraction to the nucleus. So it's more like a sound wave reverberating inside an organ pipe or the vibrating surface of a drum. And the wave function obeys Heisenberg's uncertainty principle. If you try to pin down a particle's location by trapping the wave function in a tiny volume, then the particle's momentum, mass times velocity, becomes more uncertain. Mathematically, we say delta x times delta p is greater than h bar over 2, where delta x is the spatial extent of the cloud, and delta p is the extent of the momentum cloud. It's the range in the possible values of momentum that the particle might have if you measure it. You can't make both delta x and delta p as small as you might want. Their product is always at least h bar over 2, fundamental constant of nature. The h is Planck's constant, 6.6 times 10 to the minus 34 joule seconds. And the little bar through the middle is shorthand for h over 2 pi, because that combination comes up so often. The uncertainty principle explains why atoms are stable. Even if you drop an electron directly onto a proton with zero angular momentum, it doesn't fall down and come to rest, because that would imply that delta x and delta p are both 0, which is a no-no. Instead, the wave function strikes a balance between delta x and delta p. We'll be more quantitative about this toward the end of this lecture. The proton exists as a wave function too, but there's a big difference. Even though the proton and the electron have charges of equal magnitude, the proton is far more massive by a factor of 1800. This ends up causing the proton's wave function to be much smaller in extent than the electrons. So if we want to see it, we have to zoom in. Zooming in by a factor of 10 doesn't help, though. Neither does another factor of 10. We need to keep going for 4 orders of magnitude below the atomic scale before we can make out any details. The diameter of the oxygen nucleus is about 5 times 10 to the minus 15 meters. That's 5 femtometers. At this scale, if the nucleus were a marble, the electron cloud would be the size of a football field. Now we can see that the nucleus, it's actually a cluster of 16 little marbles. 8 of them are protons and 8 are neutrons. Those are nearly the same size and mass as the protons, but without any electric charge. They're neutral. Now wait a minute. If the protons in a nucleus have positive charge and the neutrons are neutral, then there aren't any negative charges. So what's holding the cluster of marbles together? Shouldn't the protons repel each other and fly apart? That brings us to the third fundamental force of nature, the strong nuclear force. This is a very short-range force that acts between nucleons, protons and neutrons. It's a complicated force. There's no simple equation I can give you, like I did for gravity and the Coulomb force. It depends on how many nucleons are present, which kinds, whether they're spinning, and all sorts of other things. And it only acts over femtometers. Beyond that, it's negligible. Think of it this way. In a stable nucleus, all of the marbles are coated with a thin layer of glue that's strong enough to withstand the electrical repulsion. That's the strong force. Strong force is also why those marbles are rigid. The force is attractive up to the point of contact, but then it becomes repulsive. That's why it's very difficult to compress a nucleus. By this point, we've met three particles: the electron, the proton, and the neutron. Now let's meet the neutrino, which, as its name suggests, is a teensy little neutral particle. Now, at first, it might sound like the neutrino brings a nice symmetry to the family of particles. The neutron is the proton's neutral buddy, same mass but no charge. So maybe the neutrino is a neutral buddy of the electron. No, not at all. For one thing, the neutrino has a much smaller mass than the electron, by at least a factor of 1,000,000. Another thing is that neutrinos interact mainly through the fourth fundamental force of nature, the weak nuclear force. The weak force is short range, like the strong force, but it's not like any sort of glue. In fact, it's kind of a stretch to call it a force. It's more like a special power that nucleons have to change identities. A neutron can change into a proton or vice versa. For example, a neutron sitting all by itself will spontaneously turn into a proton within about 10 minutes. Now, that can't be all that happens. The total electrical charge has to be conserved. The new proton's positive charge has to be balanced by negative charge somewhere else. So what happens is that the weak force conjures up an electron along with the proton, and they sail away in nearly opposite directions. You'd expect them to be exactly opposite because in addition to charge, momentum has to be conserved. The initial momentum of a stationary neutron was 0. So you'd think the proton and the electron would have equal and opposite momenta. But the funny thing is, when you measure them, they're not exactly opposite. The reason is that the weak force also produces a neutrino that sails away at nearly the speed of light, carrying just enough momentum so that it all adds up to 0. It took a long time to figure this out because neutrinos have such tiny masses and hardly interact with anything after they're produced. You can fire a neutrino through a light year of solid lead, and there's a decent chance it'll come out the other side unharmed. For completeness, I'll add there are at least 6 kinds of neutrinos. In the case of neutron decay, what pops out is an electron antineutrino. But for us, the important thing is that whenever you see any kind of neutrino, you know the weak force has been up to something. Zooming in further, inside the proton, things get very hectic. There are quarks within a sea of particles called gluons, and everything's in motion, particles appearing and disappearing. But that's a step further than we need to go for this course. So let's just stop here and reflect on what we've seen. We've met 4 particles: the electron, proton, neutron, and neutrino, and 4 forces: gravity, electromagnetism, the strong nuclear force, and the weak one. What sets the nuclear forces apart is you only notice them on femtometer scales. In contrast, gravity and electromagnetism are long range, acting on all scales. And their force laws look similar too. They both go like 1/r squared. But there are major differences between gravity and electromagnetism, starting with the fact that electromagnetism is much stronger. Say you have 2 protons separated by some distance r. What's the ratio between the force of electric repulsion and the force of gravitational attraction. To find out, we divide the Coulomb force by the gravitational force. The r-squareds cancel, and then when we plug in the numerical value of all of those constants, we find the ratio is 10 to the 36th power. That's a big number. The electrical repulsion is unimaginably stronger than the gravitational attraction. But wait a minute. If gravity is really so pathetic, why is it the most familiar force of nature? Gravity is what pins us down on the surface of the Earth. We throw a ball, it comes down. But we never think about the Coulomb force, at least not until it's brought to our attention by a physics teacher. The reason is, gravity is always attractive. It's never repulsive. There's no such thing as negative mass. You might have heard of antimatter. Well, even antimatter has positive mass. Electromagnetism is different. The particles that play that game can be positive or negative. And when they merge together, the result is neutral. It doesn't feel any electric force. So what happens is that all the positive and the negative charges in the universe attract one another. They quickly find each other, getting pulled together with tremendous force, forming tiny structures with no net charge, atoms. That's why the incredible strength of the electric force is hidden from us. Richard Feynman once compared this situation to a pair of Olympic arm wrestlers pulling on each other's arms with tremendous force. They're equally matched. Their clenched hands aren't moving, and so from far away, you might not even be aware of their intense effort. It's just like the proton and the electron pulling on each other inside the atom. Once neutral atoms form, all that's left of the electric forces are the slight imbalances that arise because the negative charge, the electron cloud, is more spread out than the positive charge, the nucleus. In fact, what we perceive as everyday forces, our feet pushing on the ground, our hands pulling on a rope, our knuckles knocking on a door, all of these are complex manifestations of the residual forces that are left over from the combination of electromagnetism and quantum theory. Gravity, on the other hand, never gets canceled. That's why, when we zoom way out to astronomical scales, gravity is the dominant force. That's why gravity, weak though it is what sculpts the properties of planets, stars, and galaxies. There's something else we need to know about electromagnetism. It's more than just attraction and repulsion. There are magnetic fields. They come from moving charges. And there's electromagnetic radiation, which comes from accelerating charges. Whenever you accelerate a charge, you speed it up, slow it down, whirl it around, it radiates. It takes some of its own energy and flings it outward at the speed of light. The radiated energy takes the form of photons. We will have lots more to say about photons throughout this course. In the time remaining, let's do one more order of magnitude calculation. We're now in a position to understand why atoms are as big as they are. Why are they 10 to the minus 10 meters and not much bigger or smaller? So imagine letting go of an electron and watching it fall toward a proton. It accelerates as it falls, causing it to radiate and lose energy. As we discussed, a more accurate picture is an electron cloud that's contracting around the proton. So the radius of the cloud, r, is shrinking. And because it's losing energy to radiation, the cloud will end up with whatever size corresponds to the minimum possible energy. And what would that be? How do we calculate the minimum possible energy? Well, if the electron were a classical particle, the energy would have two parts. First part is the kinetic energy, a positive number, which is usually written 1/2 mv squared. For this problem, it'll be more useful to write it in terms of momentum, p. We can do that by inserting v equals p over m, giving p squared over 2m. The second part is the electrical potential energy. That's a negative number that varies as 1 over r. In quantum theory, the electron cloud extends over a range of r and has a range of possible values of p. But still, for any particular combination, this equation for the total energy still holds. Now, to minimize E, we should keep P as low as possible. That'll reduce the kinetic part. And we should also make R as small as possible because that'll reduce the potential energy. It will make it more negative. But we can't make both R and P arbitrarily small, remember? Professor Heisenberg won't let us. If the cloud has a radius of R, the uncertainty in the electron's position is on the order of R, which means the uncertainty in its momentum can be no smaller than h bar over 2 divided by R. So, if we shrink R too much, the momentum goes up, and the kinetic energy term grows out of control. But if we increase R too much, the potential energy rises, and it starts to dominate. To get the minimum energy, we need to balance the kinetic against the potential. Let's work it out. For P, we'll insert the minimum possible value of h bar over R. Now, officially, it should be 1/2 h bar over R, but this is just an order of magnitude calculation. We haven't been precise enough about the meaning of delta x and delta p to justify worrying about factors of 2. That's why there's a squiggle in the equation instead of an equal sign. Throughout this course, a squiggle means has the same order of magnitude. With that substitution, we get E equals h bar over R squared over 2m minus eta E squared over R. That's a function of one variable, R. So one way to find the minimum is graphically. We can plug in the numerical values of the constants and then plot E against R. Let's use a logarithmic x-axis to help us see what's going on. For small values of R, the 1 over R squared term is dominant, causing the energy to shoot up as we approach 0. But for large values of R, the negative 1 over R term is more important. That causes the energy to rise from negative values towards 0. And in between, there's a minimum. The minimum occurs when R is about 1/2 of 10 to the minus 10 meters. That's 0.05 nanometers, which is about equal to the observed size of a hydrogen atom. So the calculation succeeded in explaining the size of the hydrogen atom. Those of you who know calculus can also locate the minimum through a direct calculation. You take the derivative of the energy with respect to R and set it equal to 0. You'll find that at the minimum, R equals h bar squared over eta m E squared. That combination of constants comes up so often in atomic physics, we give it a special name, the Bohr radius, and a special symbol. It's an A with a subscript of 0, A0. Its value, as we've seen, is about 1/20th of a nanometer. What about the value of the energy? That turns out to be minus eta E squared over 2A0, which has a numerical value of 2.2 times 10 to the minus 18 joules, as shown on the chart. That energy scale, too, is central to atomic physics, so it's useful to express it in different units, electron volts, or eV. 1 eV is defined as 1.6 times 10 to the minus 19 joules. That way, the minimum energy comes out to be minus 13.6 eV, which is indeed the measured binding energy of an electron in a hydrogen atom. So now we understand the sizes of atoms and their energies. The combination of Coulomb's law and the Heisenberg uncertainty principle singles out characteristic size for atoms, the Bohr radius, and a characteristic energy for the electrons, a few electron volts. Let's return now to that chart of distance scales that I made in the last lecture, which ranged from the radius of the Earth to the size of the observable universe. We'll add the 3 key units that we discussed during our zoom in. We have the micron, a millionth of a meter, same order of magnitude as the wavelength of visible light. We have the Bohr radius, 5 × 10 to the minus 11 meters. That's the atomic scale. And we have the femtometer, 10 to the minus 15 meters, the nuclear scale. Well, this was quite a journey down to the nucleus and back again. And it brings home a broader point. The word astrophysics makes it sound like it's a subdivision of physics. There's atomic physics, there's nuclear physics, and then there's astrophysics. But I think that's wrong. Astrophysics is the concatenation of all of physics. We're going to encounter phenomena that involve gravity, electromagnetism, atomic and nuclear physics, and even, as we'll see at the end of this course, laws of physics yet to be discovered.